Good morning. I am Devasena. In this lecture, we are going to discuss about loop analysis or mesh analysis. This topic is present in the subject circuit analysis. Before going to discuss about the loop analysis, let us start discussing about the Kirchhoff's voltage laws. In any network, the algebraic sum of the voltage drops across the circuit elements of any closed path, that is a loop or mesh, is equal to the algebraic sum of the EMFs in the path. In other words, the algebraic sum of all the branch voltages around any closed path or closed loop is always 0. Around a closed path, the sum of voltages is equal to 0. The diagrammatic representation for the Kirchhoff's voltage laws is shown below. Here, the sum of all the voltage drops around the loop is equal to 0. We have 4 voltages in the closed path. The voltages are V suffix AB, V suffix BC, V suffix CD and V suffix DA. According to the Kirchhoff's voltage laws, the sum of all voltages, whether it is a drop or rise, is equal to be 0. Now, the Kirchhoff's voltage laws state that if one traces at a starting point of a closed path and goes on tracing and noting all the potential changes, either drops or rises in any one particular direction till the starting point is reached again, he must be at the same potential with which he started a closed path. Let us start discussing about loop analysis or mesh analysis. Loop analysis is especially useful for the circuits that have many nodes and loops. The difference between the application of Kirchhoff's laws and loop analysis is, in loop analysis, instead of branch currents, the loop currents are considered for writing equations. Another difference is, in this method, each branch of the network may carry more than one current. The total branch current must be decided by the algebraic sum of all currents through that branch. While in analysis, using Kirchhoff's laws, each branch carries only one current. The advantage of this method is that for complex networks, the number of unknowns reduces, which greatly simplifies calculation work. Consider the network shown below. There are two loops, so assuming two loop currents as I1 and I2. This is the representation for the loop analysis. While assuming loop currents, consider the loops such that each element of the network will be included at least once in any of the loops. Consider branch BE. Now, the branch BE carries two currents, that is, the current I1 from the point B to E and the current I2 from the point E to B. So, net current through the branch BE will be I1 minus I2 and the corresponding voltage drop across the resistance R3 must be shown in the figure below. This is the representation. In this first diagram, we have considered the current is flowing from the point B and it ends towards E. Therefore, the net current flowing through the resistance R3 for the first diagram is I1 minus I2. Consider the second diagram. In the second diagram, the current is flowing from the point E and it flows to resistance R3 and it ends at B. Therefore, the current flowing through the other direction. So, the net current for this will be I2 minus I1. Now, while writing loop equations, assume main loop current as positive and remaining loop current must be treated as negative for common branches. The diagrammatic representation of a single loop, writing loop equations. For the loop A, B, E, F and A, the equation is minus I1R1 minus I1R3 plus I2R3 plus V1 is equal to 0. For the loop B, C, D, E, B, the equation is minus I2R2 minus V2 minus I2R3 plus I1R3 is equal to 0. By solving above simultaneous equations, any unknown branch current can be determined. So far we have discussed about the theory related to the loop analysis. Let us start discussing about steps for solving problems loop analysis. Step 1. Choose the various loops. Step 2. Show the various loop currents and the polarities of associated voltage drops. Step 3. Before applying KVL, look for any current source. Analyze the branch consisting current source independently and express the current source value in terms of assumed loop currents. Repeat this for all the current sources. Step 4. After the step 3, apply KVL to those loops which do not include any current source. A loop cannot be defined through current source from KVL point of view. Follow the sign convention. Step 5. Solve the equations obtained in step 3 and step 4 simultaneously to obtain required unknowns.